Hi, this is ET370 Lecture 4. It's going to be a two-part lecture. In the first part, we're going to cover pulse width modulation, or PWM, and then cover why pulse width modulation is needed and how can we implement it. We'll actually implement it with this new device called a transistor. These are very special devices, and we'll talk about some common types here. And then we'll look at the specific one called the bipolar junction transistor, or BJT. And in this first part, we'll look at NPN, PNP, and the water analogy. In the next lecture, or next part of this lecture, we'll look at 4 different states and get some more understanding on the NPN one. But let's just look at this first half. So pulse width modulation. All right. So the idea is, let's say you have a scenario where you have a battery, okay, something that has constant voltage, and you have some load, a light, a motor, whatever it is. And the idea is, well, in this case, if I have a switch and I close the switch, I'm only going to give full blast power to this load, right? Or I'm going to give zero. I'm going to either turn it off or on, kind of a binary situation. And the question is, what if I want something that's variable? What if I want to vary the output voltage here so that I get some kind of selectively desired voltage, right? Or brightness or motor speed, okay? So the concept would be, can we use a high speed switch and achieve that and actually open and close the switch very fast in a specific way so that this simulates like it has a variable voltage and variable current. Okay. Now, mechanically, this is going to be difficult, right? If I have literally me pushing a mechanical switch to try to do this is impossible, right? You're going to have this herky-jerky motion, herky-jerky voltage and current on your load, right? But if we have a high-speed switch controlled by a microcontroller that can operate in the thousands and tens of thousands of hertz, then we can do something. Okay, so here's the concept. Here's time, and imagine you have this switch being controlled by like an Arduino, right? Or any other microcontroller. And if you could somehow close the switch and open the switch in this pattern, you might be able to get this voltage to synthetically appear smaller than it actually is. Okay, so let's look at what's going on. Notice it's just a bunch of square waves. So when you have the switch closed, this is going to allow this output voltage, so this is a plot of output voltage versus time, to equal the input voltage, right? When the switch is closed, right? You just have a short by KVL. Okay, now when I open the switch, very simple, the output voltage here goes to 0. The time between these start times here we'll call as the period, or the period of the PWM cycle. And the time that is closed is here, okay? And so notice this pattern repeats. Now, the ratio of the time closed divided by this period is called what we call the duty cycle. And what happens is if this PWM period is very small, the output will be approximately the duty cycle times the input. So for example, if I had the on time at 50% of this period, then the duty cycle is 50% and the output would be half of the input. So really cool, very simple idea, but it actually works very effectively, okay? All right, good. For the PWM, we need a fast acting switch, and a mechanical switch is too slow. It's too bulky, as I said before. And we need a switch that can essentially take a low power signal from a microcontroller and actually produce high current. And just a practical point here, or maybe a practical example is, maybe in some of my videos you hear the BART track. I live close to the BART tracks, and you hear this BART track, that hum. That's PWM. Part of that is the road noise and the friction, but that hum, especially when you're at the BART station, that startup, that's the PWM signals of the power, the electrical power being driven to the motors. So you do hear this, and what enables this is transistors. So this high-speed switch is enabled by transistors. And so here's an example of the same thing, except now you have some kind of transistor here, and you have some Arduino or microcontroller, some processor. You'll have some large voltage source, and you have a motor or some load. And now a large current can go through here enabled by this low power PWM signal, right? So this little signal is a square wave, right? And then this opens and closes like a square wave, all right? So I hope you have a big picture understanding of what's going on with PWM and why transistors are useful. Okay. So what are some common transistors? And I want you to think of three terminal devices, 1, 2, 3. One where it's a low power input signal, and then the other one is like the big power rail signal, right? Or the big power rail that's closing, right? And so the one we'll talk about in today's lecture is called the bipolar junction transistor, BJT. This is actually a current controlled device. The next one we'll talk about later on next week in lecture is the metal oxide semiconductor field effective transistor. And so this is also called MOSFETs, and these are typically voltage controlled, okay? We'll look at a complementary metal oxide semiconductor transistor, or CMOS. This is a combo of MOSFET and N-channel and P-channel. So it's just two of these stacked up next to each other. A lot of VFDs will have insulated gate bipolar transistor, and that's a combination of a BJT and a metal oxide MOSFET, and IGBT for short. It's a voltage controlled signal, but it has good power combinations, right? There's also SCRs, silicon controlled rectifiers, right? So these are all common types of transistors in your toolkit, okay? But we're just gonna focus on kind of these three, because once you learn one, like the rest are just a variant of this, okay? Okay, so let's look at the bipolar junction transistor. And remember, three terminal device, small signal in, allows a large current out between two of the terminals. Okay, so the two main types for a bipolar junction transistor are going to be the NPN and PNP. And I want you to think back-to-back diodes here. So let's look at the NPN. So in this case, the NPN has a Npn structure. And you guys remember what NPN stands for. N is the N-type semiconductor material, and P is the P-type semiconductor material. Remember, N has the extra negative or electron charge carriers, and P has the holes, right? And so we have basically like an ice cream sandwich where N and N are the chocolate on the outside, right? And so N on the top here, we'll call as C, the collector, and this middle one is the base. That's where we're going to get the low input power signal. And then the other N on this side is the emitter. Now, I know it looks symmetric, but bear with me. Okay, for the PNP, what do we have? It's just the flip, right? You still have emitter base collector, but notice the emitter part is switched, okay? All right, so the symbols, so this is just something you're going to have to memorize. These are the symbols, three terminal device on both of these. You have a circle, and I want you to notice you have this line here and this arrow. And look at this arrow on both of these. Here, this arrow is pointing out. So a nice mnemonic for NPN that I actually use is not pointing in. Okay. When we look at MOSFETs, it's actually going to switch that, unfortunately. But for BJTs, the arrow pointing out is not pointing in. Okay, what about this one? We have pointing in proudly, right? The arrow is pointing in. Okay. CBE, CBE, good. Now notice the current here. This current is, we have the base current, the collector current, the emitter current. Same with here, the base current, the collector current, emitter current, right? And the whole idea for both of these types is a small base current gives you a large collector emitter current, okay? All right, so there's some observations from these symbols, right? And this will hopefully help you memorize how to draw these symbols. You're just gonna have to learn how to memorize this, right? Okay, E is always attached to the arrow inside the symbol. You see that in both of these. E is always attached to the arrow, good. B is always the middle, right? And C is whatever leg is left over. So if B is in the middle and E is attached to the arrow, C is just what you get afterwards. Okay. Now the current, you're like, oh, how do I remember to put all these currents? Okay, it's actually not too bad. Just follow the arrow in the symbol. So if I see the arrow here, the emitter current is going to be leaving, but the two collector and base currents are going to be entering. If I look at the current here, well, the emitter current now has to be entering and the two base and collector currents have to be leaving. So that's just a way to remember. It's very similar to the diodes, if you recall the diodes, right? The arrow, the ID for a diode you always have is defined as the same direction as the diode direction, okay? So just stare at this, pause it if you have to, but got to memorize that. Okay, let's keep going. So what I want to cover here is the water analogy, right? Just so that we have some intuition. Love to have intuition. Okay, so I redrew it. I have a NPN, right? I have the knot pointing in, and I have all the arrows pointing in the same direction as the arrow inside the symbol. I have E attached to the arrow, base in the middle, and C is left over. Okay, so here's the idea. Okay, here's the idea. Imagine you have a pipe. And again, I have a three-terminal device. I have collector, base, emitter. And imagine I have a high pressure and a low pressure. High pressure at the collector and a low pressure at the emitter. And imagine this little plunger. Now, this isn't the perfect example, so I apologize, but I hope the idea gets across. Let's say I have a pressure here at the base, and hopefully this can be small enough to just pop this top up, right? Now, the idea is if I can pop the top up, a lot of current can flow around the sides of this plunger. So that is the idea, right? And so small signal here allows a large current to flow here. And this is our current controlled bipolar junction transistor, right? So I hope you guys see that, right? Okay. Now, what about the PNP? Again, these examples, these hydro examples, these water analogies, well, they're not perfect, but I hope they get the idea across. Okay, so here's, again, your PNP. Look at the arrow, look at the E, good. B in the middle. And then you have the currents of the arrows following the arrow in the symbol, good. And now notice I put the different E on top, whereas here I had C on top, right? You could think of like the NPN as normal logic and the PNP as positive logic. Now notice here, the current to get this to go actually went into the base. But here, the current is actually, we have a hinge here and this little lever. If we're able to get a small current to, like we create a vacuum, let's say, and suck some current out, well, hopefully that opens this hinge and allows a lot of current to flow from the emitter to the collector. So the PNP is just oriented in a way where both of these consistently have current or pressure going from top to bottom. But to activate an NPN, notice current is going into the device, where to activate a PNP, current is being sucked out of the device. So kind of like an opposite logic of how to drive these two things, if that makes sense. Okay. All right. So I hope this short little half lecture was instructive on figuring out what PNP is and how would we implement a transistor, a bipolar transistor, to enable a small signal here to drive large currents. Okay, see you in the next lecture. Thank you.